All right, so this week we are going to be learning about publication bias and the multiple ways that we assess for this. So let's talk about sources of bias. We have bias related to two separate sources, the first of which is related to statistical significance, and the second is related to convenience. So let's start with statistical significance. We have three types of bias here. The first is publication. So this is simply that studies that are statistically significant are more likely to be published. So it's possible, if what you're looking at is published studies, that you have some bias related to that, which could be that there are non-statistically significant studies that are out there that weren't published and you missed them. Duplication is the next one. And so this happens if you are a primary researcher and you have a good-sized database, you find something statistically significant in it, and you then end up getting multiple publications out of it. This frequently happens with folks who have huge databases that end up with great results. So you're ending up with articles that are based on the same sample of data with the same basic findings, but they are doing a recapitulation of that with multiple publications. So there can be duplications of highly significant results that are out there. And the next one is citation. So things that are statistically significant are more likely to be cited in other articles, and therefore they're easier to find. So it's possible that you're getting any or all three of those sources of bias in the studies that you've found. And so again, you found things that were published because they were statistically significant. There are possibly duplicates of the same data set, in which case, to really kind of look at this in more detail, you would look at the articles in your analysis and see if you're seeing the same authors multiple times on different studies. Then that might give you a hint. And if in the final meta-analysis and you're just searching in one search engine, it's a good idea to look through others' article reference lists to see what they have cited, which we know that that's called reference chasing. The other form of bias is convenience. So this one is much harder to get around. And the first one we'll talk about is language. So wisely, most people are only going to be looking at studies that are published in a language that they're fluent in and that they can read. So if there are a lot of studies that are done in your literature area that you are looking at, say in another language, maybe French, it wouldn't be a bad idea if you were to publish that meta if you found someone who was actually fluent in French so that they could help you code those articles appropriately, and so that you could include those in your analysis and then make sure that language isn't a variable that's causing a source of bias for you. We also have availability and cost. So what this means is we tend to code things that we can find easily and things that don't cost us anything. So luckily for us, we have an amazing library system, and we can get most things that we need through the interlibrary loan process free of cost. However, that's really not the case for other institutions, and some folks end up having to pay dearly for each ILL request that they submit. And if you think about that, having to pay for each ILL request would add up to a lot of money in the end, and it might end up causing you to decrease the number of studies that you included because you had to ILL them and you couldn't afford them based on the budget that you had. And the last one is familiarity. So here we tend to search for studies in ways that we're familiar with. So what do I mean by that? So if you typically look for studies in Google Scholar and then you go ahead and only use Google Scholar when you're running your meta, think about what if there are other studies that aren't popping up in Google Scholar and they are in EBSCO or elsewhere. And so you're going to miss them if you only ever search in the search engine that you are most comfortable and familiar with. So how do we assess for bias? The ones that are related to convenience, there's really actually no way that we can truly assess for these in a statistical fashion. The only thing that we can do here is mental gymnastics. So think. Do you have bias related to language? Did you only look at studies published in English? Do you have a reason to believe that there could be studies published in another language that might have found something different than the overall results that you found that were mainly English-based? If so, you want to make sure that you state that as a limitation in your paper. So looking at the other forms of convenience-related bias, availability and cost. Did you end up using interlibrary loan, and were there any sources that you didn't end up getting because they weren't available to you, or there was such an increase in cost that it wasn't feasible for you to fulfill those and add those to the analysis? And then also, did you search outside of your familiar zone? So did you choose additional search engines that you're less familiar with? Did you go outside of what you normally look at? Did you go through and look for things like searching through reference lists to what we know as reference chasing? So essentially, how comprehensive was your search for articles? So remembering that with the convenience piece, all you can really do here is think about it. Really think in terms of what your studies represented and what might be missing. The ones that relate to statistical significance are the ones that we're really going to focus on today. And there are ways to assess these, and we're going to go over 5 different ways. And those 5 different ways of assessing this are based on these 3 assumptions. So first, we actually have to buy into these 3 assumptions before the forms of assessment we're going to be applying will really work. So the first one of these is that large studies tend to be published regardless of whether or not they are statistically significant. So if you've got 2,000 people in your study and it wasn't statistically significant, you're still going to get published. If you had 2,000 people in your study and it was statistically significant, of course you're going to be published. What I'm trying to say is it doesn't matter what you found or how big your effect size was. Your effect size could actually be pitiful, really small. It could be in the wrong direction. It could be huge and in the right direction. Whatever the case, it's going to be published because it was a large N study. The second of these, a moderate N study, on the other hand, these are actually at some risk of being lost. So if we only have a moderate number of people that we're looking at, the larger the effect size, the more likely it will be to get published. But if it's a small effect size and we are approaching significance where it's not really statistically significant, it still has an okay chance of being published, but it might be questionable in the review process. And then small N studies that are not statistically significant are almost never published. So if it's a low N study, remembering that it's at a high risk of being lost if it's not statistically significant. And we're going to expect for those small N studies that all of the ones that would be in your meta-analysis database of those that you analyzed, if you have any small N studies, that those are all probably going to be statistically significant. And so for all these three assumptions, all of the ways that we assess for bias are related to statistical significance. And we'll talk about that a little bit more in these next slides. So how do we assess for this? You're going to be assessing three different things. So first we want to look at, is there evidence of bias? Second, what impact does the bias have on our summary effect size? And then finally, is the entire summary effect size simply an artifact of publication bias? And so the ways in which we analyze each of those three things. So when we're looking for evidence of bias, we'll actually just look at the data, and then we'll also run a funnel plot. When we're looking at the impact that the bias has on the summary, we'll actually look at Duval and Tweedy's trim and fill, and then we'll do a cumulative analysis. And then lastly, when we're looking at whether or not the entire summary effect size is an artifact of publication bias, we're going to look at the fail-safe n values, and this is also called the file drawer analysis. So is there evidence? The first thing that we're going to do is we're going to look at the data, and we're actually going to sort our data based on the standard error. And then once we're looking at the standard error, we're going to look for any patterns that are evident as to how the standard error relates to the effect size. So we're just going to look for patterns in the data, and then we're going to look at a funnel plot in CMA. So in order to first sort our data, in CMA, the way that you would do this is you would right-click on your standard error column, and this screenshot shows that it comes up as sort A to Z. This is an older version of CMA. What actually comes up now is sort low to high by standard error, so you would select that. And what that would do is that would resort your studies in order from the smallest standard errors, so therefore the most precise study, all the way down to the one with the largest standard error, which would be the least precise study. So let's look at the data in a little bit more detail. Now, looking at this from Excel here, we're doing the same thing, it's just in Excel, so I'm just going to show you this very quickly. This is our Wilson PowerPoint example. And you can see that when we are looking at our data here, you'll see our summary effect sizes are in order. So this column E here. So we start out with 0.13, we then go to 0.18, we then go to a slightly larger 0.18, a 0.26, 0.28, and 0.34. So these are all in order from smallest to largest standard error. And again, what we're looking for here is any apparent pattern in our effect sizes. So our effect size is in column C. We're looking at a Hedges G here. And we're not really seeing any apparent pattern here. They don't go from smallest to largest. They don't seem to be getting increasingly larger here. We start at a 0.39, we drop down to a 0.31, we drop down even further to a 0.17, we drop way further down to a negative 0.33, and then we go way back up to a 0.64. So these don't follow any obvious pattern, and you'll also want to do that in CMA in the same manner. So getting to a funnel plot in CMA. So what you'll do is once you are in your database, you'll click Analyses, and then you'll click this Publication Bias tab here, and that will bring you directly to a funnel plot. And I will show you what that funnel plot looks like right here very briefly. And so this is our Wilson PowerPoint example again here. And this is our funnel plot. So this is showing us our effect sizes. So it's plotting our effect sizes in relation to the standard error. And so this particular funnel plot, just looking at it very briefly and giving you an assessment of it, this actually looks good. Everything fits within the funnel here. Things tend to be fairly evenly distributed between the left and the right-hand side of our summary effect size, which is demonstrated here by this white rhombus. So there's no obvious bias that's shown here. Even at the top, we have some on the left, some on the right. We have some on the left, some on the right down here, and then same further on down on the left and on the right. So we've got a decent spread between the two sides, and I'll talk a little bit more about the steps that lead up to reading this in just a few moments. So what impact does bias have on our summary effect size? So we're going to start with Duval and Tweedy's trim and fill, and then we'll talk about the cumulative analysis. And both of these analyses are only available in CMA. So when we're doing trim and fill, this is actually going to be the first step that we take before we go to our funnel plot, because our funnel plot actually plots out what we've learned in the process of completing the Duval and Tweedy's trim and fill. And so what we're doing here is we're in our analyses module, we run publication bias, we go up to the view tab, and then we click trim and fill. And that brings us up to the screen where you see this data up at the top. And then there's some other additional data that's missing, but you will have on your group's printout, you will see that it is asking for whether or not CMA should look to the left or to the right of the mean in the program. And so you have to tell it whether you should look to the left or the right of the mean. So here in this example, I'm actually using a different example than the Wilson PowerPoint example because there were no indications of bias. I need to show you an example where there are indications of bias and how we talk about that and what that looks like here on the funnel plot. And so that's this example here that you see that I have illustrated for us. And so you'll notice that the point estimate under the random effects model of the observed value that we started out with was negative 0.33 in this example. So we're looking at a negative Hedges G. And when we're looking at a negative Hedges G, we're looking at our effect size being significant when it is to the left of the mean. So this area here to the left of the mean shows the groups that had significance, so favor for the treatment group. So where we want the computer to look when we have a negative Hedges G is we want the computer to look to the right of the mean on this side of the funnel, because this side of the funnel represents the less significant effect sizes, the effect sizes that supported the control group or showed no effect whatsoever. So why do we want it to look to the right of the mean? We need the computer to search for effect sizes that are much lower that are missing. So are there studies that should be appearing over here that are less significant that are simply not because we've missed them in some regard? So that's what we're telling the computer to do. So if we're looking at a negative Hedges G, we're going to tell the computer to look to the right of the mean. And so what we see here is we've actually told the computer here to plot the observed and imputed values. So on the last funnel plot that we saw a couple slides back, we don't have any imputed values. We only have the observed ones, okay? But you'll notice on here we have imputed values in red. And so what that means is that these three studies here in white were actually trimmed from the analysis because there were no matching studies on the equitable other side of the distribution. So it's basically showing that there's too much significance over here. There's a little bit of an overestimation of significance and there's not anything over here. So it's saying these are asymmetrical, and we need to adjust for that. We need to account for the fact that there's really not that much going on over here that's equitably distributing that. So what happens is these 3 effect sizes are trimmed from our analysis. They are then added over here on this side of the analysis, and it is recomputed, and the effect size is then readjusted. So we end up with an adjusted point estimate. So you see how it says adjusted values? We have an adjusted point estimate, and it says that 3 studies needed to be trimmed. So this is how we look at Duval and Tweedy's trim and fill, and how we apply that to our funnel plot. So basically what happened was 3 studies needed to be trimmed, and we see that these 3 were the ones that were trimmed. Here their values are imputed on the other side, and here in the red rhombus is our adjusted point estimate, our adjusted effect size based on that. So it lowers our effect size to a negative 0.26. So overall, we started with a negative 0.33, it moved it down to a negative 0.26. That's not a drastic adjustment, it's not bad. So it was only 3 studies that needed to be trimmed. So moving on to cumulative analysis. So this looks at from the most precise effect size with the smallest standard error to those with the largest standard errors. And what cumulative analysis does is it starts with just one study and it computes the effect size. Then it adds a second study and does a meta on the first 2 studies and computes an effect size. Then it adds the third study in and computes an effect size. So it's doing a meta in and of itself every time it adds a study in, so that you can see how the effect size changes as you add in additional and less precise studies. So the first thing that you need to do to get this to run correctly is to go back to the data and make sure that you've right-clicked on the standard error and chosen to sort that from low to high. Then you run that analysis, and on the bottom of your data tab, you're going to click cumulative analysis, and it runs that analysis automatically for you. And once you've done that, here is an example of what a cumulative analysis looks like. And here we're looking at the Wilson PowerPoint example. So this will show us the effect size and how that changed as we added in every single study to the meta. And so the study that had the smallest effect size, you can see here, had a very non-significant result occur. And then as we added in studies, it actually became a bit more statistically significant, and then it fluctuated back down to a less statistically significant, and then we ended up here at the end. So we started with a summary effect size of negative 0.02, and once we added in a second study, we had a 0.15, and then at the end, we were back down to a 0.15, so fairly similar. So the initial and the end studies don't really seem that disparate from one another. And so with this Wilson PowerPoint example, we're not seeing any indication of publication bias. So it's now showing that the large N studies, so it's not showing that the large N studies were less statistically significant or had smaller effect sizes, and that the small N studies had larger effect sizes. If we were seeing that, that pattern would be an indication of bias, but that's not what we're seeing here. So again, it's not showing that the large N studies were less statistically significant or had smaller effect sizes, and that the small N studies had larger effect sizes, because that pattern would be an indication of bias, and that's not what we're seeing here. So is the entire summary effect size an artifact of bias? So Although this is how it's discussed in Bornstein et al., this failsafe n can also be a measure of how non-significant or how small your summary effect size is, which is more of what we see with the Wilson PowerPoint example. So to run this, again, you'll be in the analysis module and you'll have run your publication bias, and then you'll click failsafe n under the View tab. So first, I want to talk about the classic failsafe n. So a classic failsafe n is actually based on our z-value. So how many studies would it take with an average Hedges g-value of 0 to bring your z-value down to something that wasn't statistically significant? So we assume an alpha of 0.05 and it's two-tailed. In this instance, when we're looking at a classic failsafe n for the Wilson PowerPoint example, we would only need 3 studies in this case with an average Hedges G value of 0 in order to bring the effect size down to not statistically significant. So in this instance, that's not really an artifact of bias in this case. So what we're really looking at here is this is an artifact that it's a pathetic effect size that we have. So our effect size is only 0.15. So it's barely statistically significant with a p of 0.026. So we can see our p is 0.026. If we round that to a 0.03, we're really not that far away from 0.05. So it's not surprising that only 3 more studies would bring us over a 0.05. And so this is telling us that the effect size that we've found isn't terribly robust. So in this case, the small number of studies needed for our failsafe n isn't about publication bias. It's telling us that we're not writing about anything too amazing in this case. Secondly, let's talk about Orwin's failsafe n. So Orwin did a variation on the classic failsafe n, and he wanted to look for values that were trivial instead of looking to bring it all the way down to 0. And instead of basing it on the z-value, we're actually looking at the effect size, which is really what we want to be focusing on in a meta, because it's really all about the effect size in a meta. So to us, Orwin's is even a little bit more important than the classic failsafe n. And so when doing an Orwin's, we have to change the value for one of these 2 values here at the bottom, the criterion for a trivial Hedges G or the mean Hedges G in missing studies. I actually suggest that you change the criterion for the trivial Hedges G. So getting all the way down to 0, that would definitely be a trivial Hedges G because it would have absolutely no effect. But even if there was just a little bit of an effect, like a 0.05, that's still pretty pathetic at that effect size, and it's just a trivial amount of an effect. So instead of using a Hedges G with a 0, let's change it to something that makes more sense. So something that had an effect, but it was trivial, so really not that significant. We'll change it to a 0.05 here in this area, and then we will click compute. And what this would actually give us, it would tell us 6 studies here at the bottom. So what this would tell us is, of the missing studies out there, of those 6 studies that are missing, it would take 6 of them, if their g-value was 0, in order to bring our Hedges G down to a trivial effect size of 0.05. And so that covers our publication bias lecture for the week, and I will see you in the group meetings.